and start recording. I hope these sessions were helpful in one way or the another. So I'm trying my best to. Okay. All right. So let's talk about this particular problem. How does statistical inference solve it? Okay. Let's say this is a real case study in which 48 male bank supervisors were given the same person's resume, and they had to judge this person whether that person should be promoted or not. Okay, this basically, this resume which was given to these 48 people was same except for the applicant's name. All right. And the gender. So name and gender was hidden. Name was hidden. Gender was, in some there was male and in some there was a female. Okay. So out of these 48, 35 of the 48 people mark this candidate as promoted. Okay. Now, question is, are females unfairly discriminated against? So we took a resume. Okay, given it to 48 people. For 28, out of these 48 people, for 24, the same resume was given as if it's a woman's resume, and for 24, it was given as a man's resume. The task of these 48 people was to review and take a call whether to promote or not. So the people who got the resume as male, they said 21 got promoted, while the resume which was female resume, out of 24, only 14 got promoted. Okay, do you think it's just a mere coincidence, or are female uh, discriminated against? Okay, why do you say so?
As per the probability, it should be equal, right?
Correct. So as per the probability, it could have been equal if these many people were promoted. Female should have been similar. Now the question could be, it might be just a mistake. It might be just a little bit of a mistake. Okay, so how much mistake is tolerable? That is what we are going to discuss. Okay, so the way most of these inference problems are solved by using something called inference. These kind of problems are solved by using something called a alternative hypothesis. There is one hypothesis which says nothing is going on, woman is not discriminated against, it just so happened, it's just a random. Maybe if we run the same experiment again, maybe this time the same thing might happen with the man. So that's a null hypothesis, meaning nothing is going on, it's just okay. That is null hypothesis. An alternative hypothesis is there's something fishy going on. Okay. And so basically, either we take a null hypothesis and try to see if our data is fitting into that null hypothesis, or what are the chances of something like this happening in case of a null hypothesis, or we take an alternative hypothesis and prove that alternative hypothesis is highest chance and null hypothesis has got the least chance. Okay, so that's how you basically solve the problem. When you encounter a problem of this sort. So you define something called null hypothesis H0, meaning the defendant is innocent. Okay? The defendant is innocent. All right? All right? Mitesh, are you able to hear me? Great. Great. So basically this mechanism of solving these kind of problem is called inference. And I'll show you one example on how to do that. Now, null hypothesis stands still, meaning whatever it is, it's okay. The alternative hypothesis, which says that it's not okay, there is something fishy going on, that is called alternative hypothesis. And alternative hypothesis has the burden of proof. Okay, has the burden of proof. So the way you do is you collect the present data and then you judge the evidence. And then whatever is the evidence, then you decide whether to reject or whether to reject or accept. Now, another question, a little more concrete question to all of us. So there was this drug being tested on mouse. So mice has a mean response time without drug of about 1.2 seconds. Okay, so the mice had a mean response time of around 1.2 seconds without the drug. Now, after the drug was injected to 100 mouse, we found that the mouse's behavior got changed, and their response time, their mean response time, became 1.05. Okay, the mean response time became 1.05. Okay, and along with this, they also noticed that in this sample, in the small samples, the deviation was 0.05 seconds. Okay, the mean deviation in the sample was 0.5 seconds, not 0.05, 0.5 seconds. Okay, so question is drug effective? Meaning, did drug, alternative hypothesis is that drug was effective. Null hypothesis, drug had no impact on the mice. It's a usual behavior. So which one do we accept? Alternative hypothesis or the null hypothesis? Null one. Do you think that there was no impact on the mice? No, this deviation is amongst those who are drugged. And it's a sample deviation. Okay, just a step back. When you convert a sample deviation into population deviation, you divide the number by square root of the total population. You remember there was sample size is small, right? And there is big population. So sample size is generally considered 1, and then you basically, to convert a sample deviation into real deviation of the population, you divide it by square root of the total population, which means our population deviation will be 0.05 seconds. So when we are conducting this study of mean response time, generally the deviation comes out to be 0.05. The 0.5 is a sample deviation. To convert it into population deviation, you have to divide by square root of the total population. Because if you remember, population deviation has under root n, which is total population, while sample size is smaller. Therefore, deviation has to be converted into population deviation. So yeah. So now you can read the sample deviation as 0.05 seconds. Now is the drug effective? What is our null hypothesis? Sita? Drug is not effective. Is that at 0? Null hypothesis. Alternative hypothesis: drug has an impact on the response time of the mice. Perfect.
In this case, it's the alternative
You tell me. Looking at this data, here the population deviation, meaning on an average, the population's behavior is deviating by 0.05 seconds, because zero point 0.5 divided by square root of 100 is 10, which means 0.5 divided by 10, and which is 0.05 seconds is the sample deviation on an average in the behavior of mice. So make sense? No. Question, did you understand the question?
Yeah.
Okay. So question is drug effective? Bobby, after this change of the question saying population deviation is 0.05 seconds, is the drug effective? Basically, instead of sample deviation, I'm saying population deviation is 0.05 seconds. 0.5 divided by square root of 100, which is so. Okay. So how do we compute that? Okay. So I'll go step by step. I'll take a step back and ask you this. Given a mean response time of 1.2, which is mean is 1.2, okay, and standard deviation is 0.05, what is the population that will show 1.05 as behavior? Can you use a p-norm? What population? How many percentage of the mouse? How many percentage of mouse will show a response time of 1.05 without the drugs? So we know the mean deviation, we know the deviation. Given 1.05 as the behavior, what will be the population? Or probability of total mice to show that behavior. Can we utilize p-norm? So p-norm gives us the population which shows that particular X.
What is the mean?
Mean is, you see the mean response time without the drug is 1.2 seconds. As is 0.05.
So you know what to know.
P-norm. I'm looking for probability of such, how many percentage of the total mice would be those who are showing 1.05 as response time.
Standard deviation is
0.05.
Mean is 1.2.
2. If our in the usual setting in the H0, we have to say that 1.05 is just normal behavior. So we have to find out what population will have 1.05 as the response time. Mitesh? 38? It will be far more lesser than that. Is it 0.038?
0.013. 0.38. Okay. 0.0013. Okay, if you put
yeah, that is correct.
Then it's much less.
So if you put sample deviation, population deviation 0.05, then?
It's actually 0.1%. 0.13%.
Yeah, yeah. So now, if we say that nothing is going on, then 1.05 is the behavior in the usual settings of 0.13 percentage, which is very, very low, right? So, okay. So this is the question we need to answer. Now, sample deviation is standard deviation is sample deviation divided by square root of population. Now it comes to be this: probability equals p norm of 1.05 and this. In the normal setting, as per H0 null hypothesis, the probability comes out to be 0.0013. Okay, so you look at this way: we are here, and total population to the left is 0.0013%. Now, similarly, on the above side also, there will be a similar population. Therefore, if you multiply it by 2, still there are only 3% probability, okay, 3% chances of the population which is lying in this area, which is very low. Okay, basically it's not only 3%, it's 2.7%. Okay, so effectively the as per our the H0, we are saying that the here, yeah, this is 0.3% here, right? This is correct. Yeah, this is 0.3 because only then it is 99.7%. So if you see that the chances of such a response is actually pretty low. Therefore, this H0, the null hypothesis, stands. The null hypothesis is not valid. Okay. Reason being, if we assume that null hypothesis is valid, the probability of null hypothesis being valid is so less, 0.3%. And this value is called p-value. Okay. This value is called p-value. And if you want to plot this graph, you can plot the graph like this. You can create X, some sequence, and generate Y from D norm, and then plot it. Okay? So it will come like this, and then you can. So now you can see that it's very clearly, based on these numbers, that 1.05 is definitely not possible to have a usual behavior, right? And therefore, this H1 wins, and we reject the null hypothesis. We say that the drug is effective. All right. Here I have written some commands. If you want to plot the graph, you can plot. Videsh is saying didn't get it. Okay. Should I explain again? Okay. So null hypothesis says drug is not effective, as in whatever was going on is perfect. It's just that this particular case is is part of the normal behavior. Okay. Now we computed assuming the normal behavior, assuming that the mice has the normal behavior, what is the percentage of mice that will show 1.05 response time? That's what we computed. We computed that how many percent of total mice will show 1.05 as behavior. which is hardly 0.3%. Okay. Yes. So it's not a normal behavior, and therefore null hypothesis stands rejected, and hence the drug is impactful. All right. Okay. So so this is basically, whenever we are computing the hypothesis, we basically compute the area under the graph belonging to this particular value, and that's what controls, that's what dictates the dictates whether our inference is correct or wrong. All right. Okay. So if null hypothesis is true and the judgment is also true, okay, then I mean, if our null hypothesis is true and the judgment is rejected, that means we got a false positive. If null hypothesis is false and judgment is rejected, that means true positive. And basically, these are just a keyword, false positive and false negative, that you have to understand. Okay. I hope that you all know that part. What is false negative, false positive? Okay. So or in other words, type 1 error occurs when convicting an innocent person. Type 2 error occurs when letting the guilty go free. A positive correct outcome comes when convicting a guilty person, or negative correct outcome comes when letting an innocent person go. Okay. All right. So the smaller the value, the smaller the area, meaning smaller the p-values, provide the increasing stronger evidence against H0, meaning the probability of H0 being correct is very, very low. All right. The statistical significance is of p-value is the likelihood that the result or a relationship caused by something other than mere random chance is very low. Okay. If p-value is very low, then the likelihood of the result occurring just because of mere random chance is very low. Okay. All right. So generally, if the probability is greater than 0.1, okay, it's not a significant evidence against H0. Okay. If probability is less than, in our case it was 0.0013, is less than 0.1, it is significant, marginally significant evidence against H0. And if the probability further goes down below 0.01, then it's definitely highly significant evidence against H0. In very simple word, the moment you hit 0.1 as in 10% chances, you start becoming suspicious. Okay. If you're saying it's normal, it's okay. But then you say that whatever has happened has got only 0.1%, which means sorry, 0.1 probability, meaning 10% chances and still it happened, then you start getting suspicious. Okay, that this null hypothesis that nothing is going on is wrong. And the moment it goes below, if something that has happened had a very rare chance of occurring, then definitely something is going on. Okay. All right, although it's the same thing what we have just told. So state your null and alternate hypothesis, specify the level of significance that is acceptable, check assumption only if size is small, use appropriate test to find out p-value corresponding to the data observed, and if p-value is significantly less than 0.1, then reject the null hypothesis. All right. So now there are many ways. R provides many packages to you to test the null hypothesis. Test various kinds of hypothesis testing. Okay. The hypothesis testing could be one variable, two variable. Then there is ANOVA library which provides you the to test the null hypothesis. Then there are multiple other kind of tests which are there, which can help you independently observe and test hypothesis testing. All right. One of the tests which we will use is Wilcoxon signed rank test. It's basically a library which does the testing very quickly for you. All right. So look at here. So here is some data from HSB, and what we want to find out that whether the right is a normal distribution or not. Okay, our H0 hypothesis is that it's the right data, that particular data is not normal distributed, but it's a random data. Here, this Saprio test or this also what do you call Wilcoxon test. This is the Wilcoxon test, which basically tests hypothesis that a data is normal or not. Okay, so let's have a look at it if you want to. So here there are a few more things which are of significance to you. One is this data you see. This data is getting downloaded from a website. Okay, do you want to try it as I'm trying? Okay, so what has happened? Oh, I was supposed to. All right, remove the comma at the end of it. No, actually put this also. Ouch. Okay, so let me just I'll paste it again. Okay, you want this, right? So all right, so we are loading the data from that URL and we are marking it within this data. What we are saying, create this, which is a factor, and we are loading it into prog. Okay, now if you say HSB2, you can see that. HSB2 has this data. It has got one column called SCH type. Okay, SCH type, other column as program, and one column called race, and so on. Okay, now we want to find out in this column called right. In this column called right, is the data normally distributed? So quickly, how did we do this? We used to say hist, right? and it would show us the diagram. You can see that the data is actually kind of normal distributed. Okay, kind of a normal distributed. Little left skewed. Okay. Also, we can check the summary statistics. Summary is a very important function. So other ways attach HSB2, and now these variables called write will be available locally. So whenever you say summary, it gives you multiple things. First is it gives you min, max, it gives you median and mean. It also gives you first quartile and third quartile. Okay. Okay. Now, the moment you say Sapiro.test, it tells you that the chances of it being the normal data is this much. Okay, chances of this being normal data is 10 to the power minus 6. This is 9.8. Let's assume that to be 10, and 10 into 10 to the power minus 7 is 10 to the power minus 6. Okay. So the chance of it becoming makes sense is 1 in 1 million. Okay. Therefore, the data is normal. Okay. The null hypothesis says that data is nothing, data is not normal, but this says that chances of that is very low. Okay. Make sense to you, Mitesh? So instead of you analyzing it, you leave it to Sapiro, and there are multiple kind of tests. Okay. Okay. So yeah. All right. The session is getting recorded, right? Yeah. All right. All right. Should I move ahead? Hmm?
Yeah.
All right. So that completes the statistics portion. So you can use R in a lot more sense, in a lot more statistical analysis. This was just a very basic overview. All right. The summary, I think the summary also gives us the median, min, mean, max. Okay. I think standard deviation also you can compute. Yeah, standard deviation, I think I can. Yeah. So you can quickly compute a standard deviation, mean, and everything, and utilize R for many statistical works. Okay.
How to calculate mean?
What?
Mean.
Mean, you just say summary. Summary, and whatever variable you have, I'll say here, you can see that summary, or you can also find out SD, standard deviation, using this. Okay. P norm, Q norm you can use. All right. All right, so we're starting with the day 3. Here we'll talk more about data science and less about our statistics. Okay. Great. Now comes the real part which everybody is waiting for, the correlation. Given a lot of data, you want to figure out where is my data fitting, and hence how can I do predictions. So using R and using all of these data techniques, you can do a lot more predictions than you could have. You can actually, looking at the data, you can't really realize that there is a graph that is fitting into this data. So how do you generally do the predictions in Excel or something in normal life? In as of today, if you have to do some prediction, you are given say last 10 years data on IBM that the in 2002 this was the output. In 2003 this you are given this data. Now quickly you have to predict how much it is going to be this year, say revenue for a company.
It will be with a trend.
Trend
On the previous, whatever the trend was playing on the previous year income. Previous year data.
Okay. So there's a function in Excel for that.
I don't know, there is a function, but you normally draw a graph.
Okay, you are saying you'll plot a graph and then figure it out. Okay, so rather than doing it manually, this one fits the graph and gives you the billion predictions. It's called linear regression. You have given a good set of points in your graph. You have to fit a line. You have to fit a line which is like best fitting line in this. Okay, and if you try to do it manually, it's almost impossible. Okay, that's where the computers come into play, and so that's where the correlation plays a very big role. Specifically, when your data is say a million record, so up to a million record, R can handle really well, while Excel cannot handle a million records. Okay, now here, so correlation is an indicator. Correlation is an indicator that with this variable is getting changed. And if it is linear, means if I change x change x by certain amount, the similar proportion will change in the dependent variable. So it should not be confused between causation and correlation. Can you help me understand what does it mean? So causation means there should be correlation does not mean cause and effect. Cause and effect, and because of this variable this happened. Okay, that's cause. Here it's a relation. It so happens that when we were increasing this was also increasing. All right. It could be, even though there is a dependent variable, using a dependent variable also we can predict the independent variable. All right. So correlation is relation between A and B. It's not necessary generally that we, in case of causation, we say that because of this is happening. Okay. Here correlation, we say these things are related by this equation. Okay. Also, the correlation varies between -1 and +1. The high magnitude indicates perfectly linear relationship. 0 indicates no linear relationship. Okay. So whenever we say correlation, we try to figure out whether there is a linear correlation between two variables. If it is 1, that means there is a strong linear relationship between two variables. If it is negative, that means there is no linear relationship. Okay, and now once we establish the linear relationship, that this is the line that is fitting these points, then we can predict the other variables. Okay, so let's look at this diagram. Look at this diagram. This is ordinary least square estimation. What does OLS means? OLS means that what we do is we take a line, big line, we try to fit it in, and we keep on switching the slope. We can try to fit this line into this data. We start fitting this line into this data such that the distance between the actual and actual value and the current line is the summation of these distances. So we are trying to fit this line, right? And there is this distance, there is this distance, there is this distance, there is this distance. The sum of squares of these deviations should be minimum. The sum of these distances, sum of the squares of these distances should be minimum. Only that particular line will fit into data. So we take this line, we keep on changing this and try to fit it in such that the sum of squares of these lines should be, of these deltas should be minimum. Okay, this is the projected line. That this line is what we are projecting. So for x value, there will be two values, one actual value and projected value. The difference between actual and projected, whatever it is, that distance, that delta should be squared and summed up. And then whatever line is resulting in that, in the overall summation, is considered as the best fitting. Okay, the one that has least total deviation. Okay, so to do this manually, it was almost impossible, and that's where the programs gave us a great value. Now look at this diagram. Look at this diagram. It's saying that in year 2000, the rates were something, 2001, 2002, and so on. Now let's say we want to do the prediction for 2005. Okay. Okay. So how would you do that? So first, what you do is we load this data, we load years into year and rate into rate, and then plot it. After plotting, we can review quickly that, hey, this data seems to have linear relationship. Okay. Now to confirm linear relationship, you can say COR and year and rate, and that will confirm, that will tell us that how great is our linear relation. Okay, so you can see that COR, year and rate. You can see that. Okay, so you can see that the value is almost closer to 1. Negative value means it is inversely proportional. As the years are increasing, the rate is decreasing. It is closer to 1, very close to 1. That means it is a linear relationship. Make sense?
Closer to -1.
Yeah. So -1 means it's a negative relationship. Okay. Okay. While negative indicates opposite, means if you increase rate is negative. As you can see that the slope is negative in this diagram. All right. Now, how do we actually solve these kind of problems? It's very simple. All you need to say is fit equals to LM rate versus year. That's all. I'll show you can see that. So you can say fit equals to, okay, now it is showing us the slope. How do we geometrically, how do we specify a line? 1 by slope plus an intercept, correct? So when we say LM fit equals to LM rate versus year, it gives us the slope. And now, once we know the slope, we can do wonders with it. Okay. Now, you can actually try to fit it in for, say, year 2002. So for year 2002, our value should be 7.798. Okay, and what is our value? Our value is, let's go back, 2002, our value is 7.62, and here it's 7.79 with 7.8. So the difference is only 0.2. Okay, you can plot year versus rate, and you can see this, and on top of it, okay, and you can fit a line into this. Now you can see that using AB line and plot, both of these things will get plotted together. So basically, without doing any mathematics, without doing any maths, we were able to predict, we are able to fit a line. Now we can do the prediction easily. The way we did a prediction for 2002, we can also do the prediction for 2014. Okay, 2014 says that it will become minus 0.662. All right. Make sense?
Yeah.
All right. Any questions here?
But this AB line not coming.
What?
AB line. AB line is not coming.
Why? AB line. So Pritpal has joined. Mitesh has joined. Hi Pritpal, can you hear me? So let me make you the presenter. Yeah. What error are you getting? Press Control L.
Control L. Okay.
Now say. Yeah.
Like this.
Yeah. Say AB line.
AB line. E.
No. Fit. Yeah.
Should show line, right? Yeah.
Yeah, it should show. Do you have any window open or something?
No.
Say plot again. Say window. Brackets. No, just like without any year or anything. Oh, without say window 6,7. 6,7. Some other problem is there. Maybe you have to say 6,6. Say 6. All right. So your problem is why the fit is not happening, right? you generally say width equals to something, height equals to something.
Okay, only 2 parameters.
Yeah. All right. Control L. Why that thing is not happening? Plot. Do plot again. Now AB line. Fit. Just check help AB line. Maybe you need to check color, change color or something. Scroll down, check if there is some color argument.
Wow.
Okay. So we'll just see to that later. Maybe some check any other machine, anybody else's results. Okay. So you were able to correlate it.
Yeah. Calculating fit, right?
Yeah.
Yes.
So you got coefficient called this thing intercept and the constant.
Yes, sir.
Using those, you can basically compute the further feature values. Okay. Now moving ahead. All right. So this was a normal simple linear regression. Okay. Any questions on this? Very straightforward. All you have to say LM rate tilde year x tilde y, and then you get the result. It's as simple as that.
Yeah, no, I got it.
What?
Line, I got it. Actually, I did the reverse way, that's fit the calculation. LM, year.
Oh. Yeah. First, you have to say the dependent variable and then independent variable. Okay.
Okay.
So this was okay. So this was the easiest thing to do. Now the complex thing starts. Imagine that you are running a factory and you have hundreds of variables in the factory, and then there is something output. So you have got output y and you have got some x1, x2, 100 variables. Now you want to find out what exactly is the relationship between x1s and y. And it could go very, very complex, and normal methods cannot do these computations. Okay, that's where the multiple linear regression comes into play. Earlier, in case of 2 points itself, fitting a line was tough thing. All right, see you then. Okay. So multiple linear regression means having multiple variables which are linearly dependent on one. Okay. So our outcome is dependent on multiple variables linearly. Okay. It only captures the linear dependency. All right. So these are the features x1, x2, x3, x4, and this is the outcome, which is y. And for various values of x1, x2, various combinations of x1, x2, x3, we get y. Beta 1, beta 2, beta 3 are our coefficients, and epsilon is our error. Okay. So the assumptions in multiple linear regression is that residual errors should be independent. Errors should be normally distributed. Residual errors as in when we compute our y for x1, x2, x3, the difference in the y should be the summation of the residual errors should be independent. Okay, and errors should be normally distributed, and mean of these errors should be 0, and errors should not exhibit autocorrelation. There should not be, error should be fairly, when we are computing, right? So we'll be doing approximation. These are approximations. So whenever we do the approximations, the actual value and the given in the data, y will vary. Okay, so we will have to compute errors, or we'll call them residuals. So residuals is nothing but actual minus the one which is coming from our curve fitting. Okay, so coefficient of determination r square can give you an indication of good fit. It indicates how well the regression line approximates to the real data. Okay, if r square you get as 1, that means the data is fitting really great, and it is also used as a criteria for choosing between multiple models. Okay, and the principle here applies is you might have multiple equations, multiple models fitting your data. You should generally choose the one which is the simplest one. Okay, sometimes highly correlated independent variables interact with each other, and thereby rendering the ordinary least square methods imprecise. In such cases, including an interaction terms may increase the performance. Okay, you might have to induce more terms, and if you include more terms, what happens is the main effect of the variables goes useless, and thereby it complicates models, and hence it loses the parsimony. Okay, parsimony means the simplest model basically. Okay, now let's try to do a hands-on exercise on one of the examples. Okay, let's say there is industry, there is a factory which is where stack loss is happening because of airflow, water temperature, acid concentration. Okay, so if you look at the data called stack.loss in R, you will see that we have stack.loss. Okay, so you can see stack loss. So stack loss has this data, this relationship between flow, temperature, and concentration against loss, and we can compute the relationship between these 4 variables using MLI. Okay, multiple linear regression. Okay, now, so is this data clear to you?
Yes.
This data here, the 4th variable is the dependent variable. These are independent variables. The diagram is fairly simple. First, so here is all we need to do is the way earlier we said x tilde y, we can say the similar thing here, saying stack.loss tilde, first variable, second variable, third variable, and comma data equals to stack loss. Okay, so I'll show you that. Okay, so let me just take this. Let me convert it to a single line. Okay, so here I'm saying stack loss.lm equals this. Dot means nothing, but it's a part of the variable name. Okay, and here new data, we are saying that can you do the prediction of stack loss when our airflow is 72, water temperature is 20, and concentration is 85. What will be the actual prediction of the stack loss? So we create a new data frame like this. And now once we have created data frame, we can use predict function to produce the predictions. Okay, it says that the stack loss for this data, this airflow, this temperature will be 24.58, 24.58, somewhere here. Okay. All right. Now, coefficient of determination can be computed using summary of stack loss and I square. Okay. So it's less. It's around 0.9. All right. So the other hands-on exercise could be that we take a package. Where is the? How do you hide the? Okay. So here, let's say we have this data. Let me also change my folder here. Okay. We can say here session and then set the working directory. I can say choose working directory, and I'm setting the working directory to my examples. All right. Now, once I have done that, I can load this data and say str clock underscore data. It shows us the various information about our data frame. Str, okay. It shows our header, what is the name of header and all that. Or we can also say clock underscore data like this. It shows us there are 3 columns: age, bidders, and price. Okay. So age and bidders should have a relationship with the price. Now, quickly we can have a look at what is our age. The summary of clock data dollar age. Why it's not working? Age is capital. Okay. Now you can see that clock underscore data dollar age is this much. If you want to see the summary of this one, what does summary do? It gives us min, max, average, and everything. Okay. Similarly, all right. For bidders, this is the minimum. 5 is the minimum. Maximum is 15, and mean is 9. Median is also 9. Okay. Then you can also do things like find the price of summary. Okay. Now, find out whether there is a correlation of this or not. To find the correlation, what you need to do is you need to, okay. So it says that there is some correlation, okay. There's some correlation between the 3. All right. So pair shows us the graph between various parameters. See that? Okay. So this graph is between age and the bidders. This graph is between age, okay, and I think so age and price is this graph. From 800 to this, 800 to this, Can you open your data? Like here. And here price to this one, it goes like 120 to 140. Yeah, I think it is that way only. So ideally, these two graphs should be either inverted to each other. All right, we'll see to that later. Okay. Now we can start correlating individually. Here it shows that there is a strong correlation between bidders and bidders, age and age, as in that's a 1. Okay. Now the relationship between age and price is quite strong. Okay. The relationship between age and price is quite strong. Okay. We have to make everything capital. So you can see model 1. And if I say model 1, okay, and summary of model 1 is this. Okay. Okay. Similarly, model 2, we can compute the relationship. Okay. So residuals, there are so many residuals, and minimum is 485, maximum is 541, and median is 30.75. That shows that there is no relation between price and bidders. There is no relation between price and bidders. Now let's see if there is a relationship between these things. We say price, we say age, we say bidders, right? We say bidders, and then we say summary of model 3. Okay. Summary of model 3. This is still better because these min and max are still less than our previous model. Okay. And residual is 139, 133, and so on. Okay. Now let me just check what is the residuals, RES. These are the residuals. Plot the residuals. Is it this? And the residuals, as we were saying, residuals should show a normal distribution. Okay. While this test says that no, it's not normal because p-value is 0.12, which is 12%. Okay. Therefore, our null hypothesis is okay, and therefore the data doesn't seem to be having a correlation. In case of box Pierce test, again the another test also fails, says that H0 is good. Okay. Now we can add something called an interaction by in this way. Okay. By adding one more parameter, which is a function of age and bidders. Okay. So I have tried to now include one more parameter, third parameter. Maybe price has got a relationship with A's and bidders multiplied together. So we are adding one more variable, and then we see if there is a correlation. Okay, looks like this time it is good. You can see that p-value is 2.2 10 to the power minus 6. Okay. Okay, now we can see that model 4, again, let's say model 4, the one which we have just prepared, model 4 dot residuals. Okay, and we say history, we basically say, okay, so you can see in this model, the graph seems to be kind of a normal distribution. Okay, here we can say Shapiro dot test. Okay, it says that no, it is still wrong. It is still did not fit. Okay, okay. So it did not. It says that p-value is 0.74. That means it's not it's not our. Okay, just a second. I think I'm missing something. Residuals, residuals, and I say model 4. Model 4 is the one which we are doing, right?
Yes.
And we say new RES. So this is my hist of RES. Although this looks like a normal distribution, we can try the Shapiro test. Where is our Shapiro test? Here. Yeah. So p-value is still 0.74. Therefore, this relationship is also not very valid. Okay. So basically, none of our model have worked out in the second example, while first example was fine. You getting my point?
Yeah.
Okay. While in the first case, when we had this model, okay, when we said, where is the first model? Not this one, previous one. Here, in the previous example, here what we had done is, we had said stackless.lm, okay, and if we say residuals, residuals of this is this much, and we can also say here Shapiro dot test on the residuals in the previous case. Now here it says p-value equals to 0.81. No, actually p-value in this case should be, yeah, this is correct actually. When the p-value is higher, right, it looks like here it looks like that h1 is considering that one. Okay, all right, nobody's. Now what does box say? All right. Anyway, so this is the way we can basically do the linear multi-regression by using LM, by plotting the graph of the residuals, and also by computing the predictions, future predictions, using whatever we have learned so far. Okay. You want to take a break?
Yeah, I'm very good sleepy.
All right.
So, till what time will we reach today?
I'm just hoping for 2 more hours.
2 hours.
There's a lot of interesting stuff coming up.
Yeah.
It's a very interesting stuff coming up. Because that's the crux of the whole learning, what we are doing right now. The machine learning part now. We'll go through few examples. Hi, Pritpal and Mitesh and Sasikant. Can you hear me? All right. All right. So we are about to start now. All right. Great. Thank you, Pritpal. And great. So now we are starting a bit about understanding the overview of machine learning. Although this will be covered again in the data science or machine learning class, but uh, we'll just go through the overview plus one hands-on, a very small example, and that should give you an overview on what all various libraries can do for you. Okay. All right. So before we move forward, let's understand what is machine learning. Machine learning we have already covered in the earlier session, that right now the way we were doing, right now we were trying to do a linear regression or multilinear regression. And the problem with this approach was we ourselves has to do our homework and figure out whether the variables are related, not related, should we introduce one more variable or not, and then we plotted the graph and whatnot. So there was a lot of manual intervention required to do the predictions. Now, machine learning approaches completely change that model. Machine learning approaches say that you don't bother about data, you bother about what do you want. Okay. And you focus on collecting the data, cleaning and representing the data rather than correlating. Leave it to machine learning approach. So the first machine learning approach is supervised learning models and unsupervised learning models. So there are two kinds of learning models. One is supervised and unsupervised. Supervised means there are input variables, there are output variables. And we try to classify, we try to correlate these input and output variables. Okay? Classification and regression are the kinds of supervised learning. For example, in classification, what does it mean? The way in case of regression, we said, what will happen to our stack loss when the variables are A, B, and C? So that was our regression. Classification is, given an email, does it classify to become spam? Does it classify to become promotion? Okay, so that is classification. So given an input, predicting the output is the classification, similar to regression. Unsupervised learning models are strange in the sense that we do not have to provide input and we do not have to provide the output variables. Okay, we just give the data and say that correlate. And correlation, we can say that find the underlying structures in this data. And what kind of structures are we looking for? We are looking for segmentation, meaning dividing the data into segments or clustering them or finding some sort of association between the data. So classification and clustering, while on one model, you have the classification giving the input, predict the output, that is classification. Clustering is divide the data into segments or clustering of the records that have similar pattern of input. Okay, so that is the difference. In machine learning models, it is a bottom-up approach. You have the data, you clean the data, you try to relate the data, and then give out. In statistical learning models, machine learning models is a bottom-up approach, and statistical learning is top-down. instead of understanding it top down or bottom up, understand that in case of machine learning model, we focus upon what do we want. In case of statistical learning model, we focus on what we have, okay, and then we clean it up. Machine learning models involves interrogating the data for information. In statistical learning, the model is involved a theory about possible relationship in two variables. So the machine learning model, the beauty of machine learning model is it automatically figures out. We do not have to fiddle with the data. Instead of users doing various kinds of determining the method, okay, here it's determined by the system machine. In statistical learning, you form the hypothesis, then you validate that hypothesis and all that. Okay, machine learning models are typically require large data set to work upon, and works with smaller data set as well. Okay, so what did we understand from this discussion? In statistical modeling, you need to put a lot of effort. In machine learning approaches, you don't need to put that many effort. Okay, in statistical approaches, you can live with small data, 100 records, 200 records, 300 records. In machine learning models, you might require something like 10,000 records to start with. All right. Let's take an example of unsupervised learning first. Okay. Let's say cluster analysis. In cluster analysis, the task is to group a set of objects in such a way that objects in the same group are more similar to each other than those in other groups. All right. So this is a great exercise. If you are with me, please pay attention because this is going to be very important to us. Okay. So under clustering, when you are doing clustering of data, there could be multiple kind of clustering. One of them is hierarchical. What does it mean by hierarchical? We form the tree out of the data automatically. In the tree, the data which is coming together under a single parent will have more similarities than the other parent. Okay, something like what Darwin did. What Darwin did, looking at all species, he formed a correlation. He formed a chart. He formed a hierarchy saying that the humans and monkeys belong together. They come from the same parent. Okay, so forming the hierarchy was a brilliant thing done by people like Darwin, right? He took his whole life and there were multiple researchers to do the same thing. Now, if the same data is available to you today, okay, same data is available to you today, even if you have no knowledge of biology, you can create the graph very quickly. I'll show you exactly that way. All right. Now, this is what we call hierarchical. There are the hierarchical cluster analysis could be done in two ways. One is called agglomerative. It's a bottom-up approach. Each observation starts in separate cluster, and then pairs of the clusters are merged to move the hierarchy. So we keep on forming the clusters and then connect. The order of complexity is n to the power 3. This is something you need to note, that these kind of analysis takes a lot of computing. Second algorithm is top-down approach. We keep on dividing the data and try to fit it with one another. Now again, look at the complexity. Look at the complexity. If there are one record, it will take 2 iterations. If there are 2 records, it is going to take 4 iterations. And if it is 100 records, now you can't imagine. Okay? So as the records grow, the divisive strategy keeps on becoming so complex, while n to the power 3 still is acceptable. Now, the way it happens is, this is so what we need to do in hierarchical clustering is, given this data, we have to form some sort of cluster. So it will form this kind of a hierarchical tree. This is called a dendrogram. This is called a dendrogram. Given unstructured data which has no correlation, we have to form dendrogram. Let's have a look of what we are trying to do. What we are trying to do right now is, given lots of cars, we want to form a hierarchy. We are given hundreds of cars, and we have to compute if there is a hierarchy existing. Meaning, you can see Cadillac and Lincoln, these two cars are very close to each other than the Chrysler. Okay, so going back to the actual data, here is the data. This is the data you have about all the cars. You see that there are 32 cars, and these are the various parameters. Okay, so first, before we move forward, before we get into the clustering, first we have to define a criteria on the basis of which we will compute the closeness of one car to another. The easiest one is the distance. Easiest one is similar to standard deviation. This is also a similar approach. Okay, we basically delta each of the parameters. So we take two cars, this car and this car, delta these things, okay, and square it. Okay, we take two cars, delta these two things again and again, and then we do the square, and then sum it up, and then compute the under root of that. So that is one approach of computing the distance of one to another. All right, let's see how far is Mazda RX4 from WAG. Okay, so let's say empty cars is there, and we are saying distance of R bind empty cars 1 and empty cars 2. Empty cars 1, empty cars 2. R bind empty cars 2. Is it binding? Names do not match. So yeah. So empty cars, what we are saying. So we are saying dist between empty cars 1 and empty cars 2. You can see that it has computed the distance between the two. Now this is doing something else. This will be better.
Oh, okay.
What? So let's say these are the two cars, okay? We want to compute the distance between the two. So all we can do is, you can see, the distance between Mazda RX4 is, and this one is 0.615, all right? Now let's take some other car and see the distance. Distance between Datsun and Mazda is 54. So that essentially means VAG and RX4 belong together. You see the distance?
So it is doing
So it is doing this minus this, this. So what is it doing? This minus, okay, let me just say A equals to, so we have A equals to, let me try to do myself, okay, A equals to this, and B equals to this, okay, C equals to A minus B, okay, and C into C is this,
okay.
and when we say sum is this, and we can say square root of this.
Okay.
You get it?
Yes, sir.
That's what this guy is also doing, not this. See, it's exact same. Okay?
Yeah.
So you did the delta, did the square. Now you could also do it by yourself.
So we can put in any way the empty car 1 or 2 and
Because it's a square, right? It's a square of values. So now, if you prepare a matrix, like this, okay? Make sense?
yes, sir. Yeah, got it.
So now, if you can prepare a matrix of one car to another, you can easily compute it. Okay, where is the sketch? Yeah. So what I'm trying to say is, imagine that you are, okay? So what you say is, my first car, say Ford, and against Ford. So what is the distance from Ford to Ford? Distance between Mazda to Mazda, okay? You will compute that distance. So you will compute this distance, this distance, this distance, this distance, okay? So and similarly, if you have more cars, say BMW and BMW. So you will compute this distance. Of course, this does not make any sense to compute the distance between Ford and Ford, okay? So we don't require this. We don't, why is it that way? Okay, so we generally don't require, so how do you say, yeah. So you find the distance between Ford and Mazda. This is not required, Mazda and Ford, this is not required because that is anyway covered. This, okay. So this is the three distances you will compute. Did I miss anything? No. All right. So if you have one more car, say BMW, Audi, okay, and we have Audi, so we will compute for Audi and Mazda, and Audi and Ford, and Audi and BMW. So we'll compute these distances where there is a tick mark, and then we'll see the order these distances, and then say that these two belong together, these two belong together, these two belong together, and then form the tree. Okay. So let's first compute the distances. Okay, so we have understood that computing the distances between the two. Yeah.
Sure.
So this is clear, right? How did we compute the distances?
Yeah.
Now, let's say, all right. So first is let's compute the distances using dist as matrix empty cars. Okay, and it will arrange the result into 32 by 32 symmetric matrix, meaning 30, because there are 32 cars, and with the element in ith row and jth row being the distance between ith automobile and jth automobile. Okay, so now let's have a look at it. If we say as matrix, so what happens?
I got some big output.
Hmm?
I got some big output.
So you'll get a really big output.
Yeah.
Okay, so you get a huge matrix, and here if you say distance of this matrix, so you'll get a matrix of 32 by 32.
Yeah.
Okay, this is a big matrix of 32 by 32, and you can see here.
Yeah.
Okay, so it basically says Fiat and Pontiac Firebird are at this distance. Fiat is at 0 distance. Porsche 9412 and Pontiac is this much distance. You see?
Yeah.
So this is our distance. We'll just store it as distance. Okay. So in 0th column, in first row, okay, in first row we have this. Yeah. So 1 is good, 2 has to be null, 1 is 1 1, 2 1, and so on. Okay. Now we have stored the distances, and now we will use a function called hierarchical clustering on this distance. Okay, we are going to use hierarchical clustering on this distance. Okay, hclust, and we can simply plot hclust beautifully like this. You can see that. Do you see that? So it has categorized all these cars together in this manner. Make sense to you? It has prepared beautifully the dendrogram, and you can see that Mercedes 280 and 280C belong together. Okay. Similarly, Fiat and so on. So it has automatically categorized. In some point when the distance between the three is equal, then it has put those three almost equal. The only difference would be it seems like it will be a hierarchy like that. All right, makes sense to you? Sounds interesting to you? So similarly, if you get all the characteristics of humans and animals across the world, you can plot the diagram like this. Okay. Similarly, if you have to do a study of all the languages, and what you do is you gather the phonetic symbols of all the languages. Say Hindi is there, English is there, and Telugu is there, Tamil is there, Kannada is there, Malayalam is there, Bangla is there. All of these languages, if you arrange in the row, and in first column, the frequency of A, frequency of B, frequency of this sound, frequency of that sound, number of vowels, if you just place them like this, and then you can actually categorize them as if you are some sort of even the linguist cannot do that kind of a job. Okay, so that's the magic of the data. There's the magic of the data. All right. So now you will be able to do the clustering, right? Now let's move to some more interesting things. Now, please understand that this is humongously difficult challenge. If the records go beyond 4,000 elements, if records go beyond 4,000 elements, it takes about 2 minutes to finish on 4-core processors. Okay, it takes 2 minutes on this. All right, now let's talk about another form of clustering called partitioning. In this, what we do is, given a lot of data, we have to find non-intersecting clusters of data. We have put the data in X and Y two-dimensional plot, and we are trying to figure out which elements belong together. It's not a hierarchical, it's a flat clustering. So the way it works is, it first selects K centroid at the, okay. So if you have hundreds of records, so what are we looking at? What are we trying to do here? Okay, imagine that you have this data. You have some value on X, you have some value on Y. You are trying to create two clusters. So it will automatically tell you that this is the cluster 1, this is the cluster 2. It will label every point whether that point belongs to first cluster or second cluster. And why did it do 2? Because we told it to. We told it that please cluster this data into 2. So how do we do that? So K means clustering means we will form K centers. We are trying to group the data in K centers, in K distances. So the way we do is, we select K centroids, K rows chosen at random, assign each data point to the closest centroid, recalculate the centroid, okay, as the average of all data points, and then we keep on doing that. Okay, and we keep on doing it again and again until we reach the end, and there will be, okay, or maximum number of iterations have reached. All right, so this is the fourth step, the assigning of data points to the clusters. This is the fourth step. What happened to this? All right. So the way we are doing is, we are given k points. We have got n number of records. Okay. We just find out first centroid, first point, or you say k random points. Assign each data point to its closest centroid. Recalculate the centroid as the average of all data points in the cluster. And these centroids are p-length mean vector, where p is the mean of the variables. Okay. So the way we are doing is, we marked these points. Say we wanted 2 points, 1 point, second point. We wanted 2 centers, right? Now just randomly. Now we find out whether this point, we pick up another point, we find out whether this new point is closer to this one or that one. Whatever is closest to, we tell that these two belong together, and now our centroid is the midpoint of these two, okay? And so slowly, this way, we will be able to form clusters. Now, I'll show you that. So let's say there was this field, okay? Now, what I will do is, how can I, like this? Okay, so imagine that we have these data points. Actually, let me just try 1, 2, 3, 4, 5. We want to find out 2 clusters. Okay, so what we do is we basically create a centroid. We just mark one of the points as centroid. Let's say this is our centroid. Let's say this is our okay. So how can I say this is our centroid? One center, another center. Okay. Now we pick up another point. Let's say this point we are picking up.
So there are no new points.
Yeah, we don't know the which group they belong to. Okay. Now we pick up another point, say this one, and we find out whether this is closer to this one or this one. So this one closer to this one, right? Yes. So we mark it like this belongs to the first, because this we have named as 1, and this is 2. Okay. Now our new centroid is the midpoint of these two, which is this. Yes. Correct? This is our midpoint. Now we pick up the second one, this cluster. Okay. Now this cluster, do you think it is closer to this one or this one? 2, right? Now let's mark it 2. We mark it 2. Okay. Now their centroid is now moved to somewhere here in between the 2 values. Okay. Yeah. Now we pick up this point. So this belongs to this cluster or this cluster? 1. Okay, let's mark it 1. Okay. Now this means now the cluster this will move to the center point, which is this centroid of this, and that one will remain there. So in a sense, we got 2 clusters. One this one, other this one. Okay, they have got this center point. This has got this centroid.
It's more towards this. This centroid. It did move towards this.
Why this centroid, first centroid? Yeah. It did move to the center?
Towards.
Because we got one number, na? Okay. So we had to find the center of this triangle.
So the triangle. Okay.
Yes.
Okay. Yeah.
Okay. So this way, this is how the clustering internally happens. Okay. Now let's try to do it practically. We are given some data and we want to find out the clustering. So this algorithm is by a scientist called Hart, Gunn, and Wong. And it partitions the observation into k groups. Summation of squares of their cluster center is minimum, meaning the way we were trying to do exactly. This means that step 2 and step 4, each observation is assigned to the cluster with the smallest value. Okay. All right. Now this was good. We were able to, the way we did here, in this example, we were able to find out two centroid, but we don't know whether this was the best case scenario or worst case scenario. Why? There could be other possible solution. We reached to this one because we started with this point. Had we here we started with this point and there we started with some other point. So if we change our starting points, what will happen? The whole mechanism will change. Okay? Whole mechanism will change. And that is why, so what we do first is, we do not change the second, we pick up the first one, okay, some corner, then we pick up the second centroid, then we pick up some other number, and then form the, so in this way, if you compute, if there are k centroid you have to select, you'll have to do k into n, or k into k, which is k cube, right? So that is why it takes a lot of time to solve these problems. All right. So to do this, let's first create a two-dimensional matrix, okay, that contains my x and y. All right. Let me just try to create a two-dimensional matrix. How am I creating it? First, I created a vector. Okay. First, here I'm saying generate my random number. Generate my random number. Okay. Using R norm. We are generating random number, 100 random numbers we are generating using R norm. Okay. And then converting that to a matrix. So now if you see, this is my matrix. And what does it have? It has got 2 columns and 100 rows. Now what I want to do is, if I try to plot this, if you see, plot X, it's a very complex graph. It doesn't make much sense. Now out of this, if I had to find, say, few clusters, what will I do? If in this diagram, I had to find clusters. This is my raw data, and I want to find a cluster. Okay, so I'm just giving them some column name. All right, so the way we do is, it's pretty simple. We say CL equals to K means cluster, and here is my CL, and it did everything. Okay, and we can say that plot X and column equals to CL cluster. Do you see the colors? Basically colored with different colors. Okay, one cluster that side, other cluster that side. Now let's just plot the centers. Here is the plot of the centers. You can see the center now. All right, so there is one cluster it has formed, and there is another cluster it has formed. So all we did was we said that, okay, so we said do a k-means on X and create two centroid. If we wanted different number of centroid, we could say things like, say, 5 centroid. Okay, now we could plot the data in the same way. Do you see that? It has converted the whole data into 5. one this, other this, other this, and then this, and then this. The color is not visible there. You can have a look at my screen from that GoToMeeting. That color is not there here. Here there are points which are not visible because of the projector, but it's visible in the screen. Can you see?
Sky blue one side.
What?
Sky blue.
Yeah.
I can see that.
Oh, maybe I'm colorblind. That's why I can see. Okay. All right. Make sense to you?
Yep.
Sounds interesting? All right. So this is the real use case of using languages like R. And this is something which is very, very difficult if you do not use these kind of tools. Okay. All right. There are many algorithms to do the clustering. We have just used the default one. I think the default one is Hartigan-Wong. Okay. We have used the Hartigan-Wong for clustering. There are many algorithms to do the clustering. All right. Okay, so till now in k-means clustering, we have assumed that each of the points belong to only one spheroidal clusters because we used Euclidean distances. But if the clusters are not spheroidal, what if we are dealing with multimodal data? Okay, this is where the probabilistic clustering works. It creates multiple Gaussian clusters, which by definition are ellipsoidal and capture all possible modal distributions. All right. So basically, this analysis will fail in case the clustering is in this form, where there might be an overlap. Okay, that's where that's where probabilistic clustering will work. All right. So okay, this is again the same thing. Yeah. So you can create two clusters using normal mix EM, and it will do basically a probabilistic clustering. Okay, and you can use the same model to for the cases when there would be an overlap due to the waves or the graphs. All right. All right. So this is probabilistic clustering example, where if you plot the historic histogram, it will be rectangular, and then if you draw the lines, it will be like this, and you can apply the normal the clustering example which we have given, and it will draw the estimates here. All right. Makes sense to you? So this is little advanced, but go through this example, and this should give you an enough amount of confidence. All right. Now, this was our unsupervised learning. Unsupervised learning as in, we did not have an output parameter, we had only the input parameters, and we had to just automatically and magically classify the data. All right. The other kind of classification problems are the supervised machine learning problem. In these problems, the goal is to predict the class of a target variable to which observation